Good day and welcome to the Big Bad Tech Channel. I'm your instructor Jim Pytel. Today's topic of discussion is battery charging. Our objective today is to discuss battery charging methods. This lecture operates under the presumption you are marginally skilled in basic DC circuit analysis, specifically basic series circuits. If you need to brush up on these skills, by all means check out the Basic Electronics 1 DC Circuit Analysis playlist available at the Big Bad Tech Channel. Additionally, this lecture is meant to be a follow-up to both the Introduction to Batteries and the Battery Discharge Characteristics lectures, both available at the Big Bad Tech Channel. If you haven't watched these lectures yet, by all means, please take the time to do so now. A brief disclaimer before we begin. Always consult the manufacturer's datasheet for the particular battery of interest. This lecture deals primarily with lead-acid batteries, and different chemistries may necessitate different charging methods and additional safety considerations. Do not assume for a moment the charging methods presented herein are universal in nature. Batteries can explode into a ball of white-hot fire or otherwise be damaged and rendered useless if you charge or discharge them incorrectly. A battery is an energy storage device, and as such represents stored hazardous energy if it is not properly locked out and tagged out. A short circuit across the terminals of a battery, be it from a conductive tool or an errant wire that bridges the terminals, can produce a high current and damage the battery. Take necessary precautions when working around or with batteries. Let us begin. Recall during the Introduction to Batteries lecture, we learned that a battery is an electrochemical energy storage device. During the charging process, a battery is supplied electrical energy, which changes the balance of charge between the chemically active materials central to the internal electrochemical reaction. The charge process converts DC electrical energy into stored chemical energy. This stored chemical energy can later be withdrawn as electrical energy for off-grid, remote, or emergency applications. If the charging process is to be efficient, effective, and safe, voltage and current must both be controlled such that batteries are not overcharged, undercharged, nor damaged in the process. Excess voltage can lead to gassing of the electrolyte. Gassing is the electrical splitting of liquid water into its gaseous chemical constituents, hydrogen and oxygen, a process called electrolysis. Not only does this produce flammable gases that must be vented, but also reduces the quantity of electrolyte and modifies its chemical composition. Additionally, if charge current is too high, the battery overheats and can be damaged. Conversely, if charge voltage and current are too low, the recharge process takes too long, if at all. This is to suggest that the charge process is a balancing act, in that voltage and current must be continually monitored and maintained between high and low limits. Further complicating this balancing act is that the high and low limits change as the battery's state of charge varies. Before we go into technical details about battery charging, allow me to use a simple analogy to illustrate the basic charge process and the various methods used to charge a battery. Let a battery represent a bucket of rocks. The volume of rocks inside the bucket represents the state of charge, and the spaces between the rocks represent inefficiencies or losses to the system. Given a discharged battery, in this case an empty bucket, one can fill it using two diametrically opposite methods. First, one could get the single biggest rock you can possibly lift and drop it in the bucket. Given that rocks aren't ordinarily perfectly bucket-shaped, one might expect this method, although rapid, to not exactly yield the best results, because there's plenty of residual capacity left in our bucket, represented by all the empty space not filled by rocks. Any more rocks this size would overfill the bucket. Additionally, a rock of this size dropped into a bucket might have the possibility of busting out the bottom of the bucket or breaking the sides. In summary, fast, but not exactly what we're looking for. On the other end of the spectrum, one could go to the trouble of painstakingly packing individual grains of sand into a densely packed, bucket-shaped structure befitting the most talented of Incan stone cutters. This method does yield a bucket absolutely packed to capacity, but takes a maddeningly long period of time to do so. In summary, full, but not exactly what we're looking for. Various hybrids of these two extremes exist that balance out our need for a reasonable charge in a reasonable length of time. One method might be to pack the bucket with a quantity of medium-sized rocks until a certain level is reached. Then return to fill the empty spaces with a quantity of medium small rocks until a certain level is reached. Then return to fill in the smaller empty spaces with even smaller rocks. This method represents a mixture of the two extreme approaches, favoring full charge at the expense of speed. Still another method might be to chuck in a couple big rocks, then toss in a couple medium-large rocks, then just let a painfully slow fine stream of sand trickle into the bucket to slowly fill all the tiny empty spaces. This method represents a mixture of the two extreme approaches favoring speed at the expense of a full charge. Note that if the slow stream of sand is ever interrupted, the bucket is still reasonably full, having taken less time than the staged approach and much, much less time than the slow trickle of sand itself. These simple analogies are meant to represent different charge methods characterized by voltage, current, time, and effectiveness. In a perfect world, a battery could be charged to full capacity fast. However, the real world requires balancing speed and capacity based on chemistry, application, time, longevity, and of course, economics. The charge process is characterized by interrelated properties of voltage and current. As previously stated, one of the hard upper limits imposed on batteries is that of the gassing voltage. The gassing voltage is the voltage at which electrolysis begins and water is electrically split into its gaseous constituents, oxygen and hydrogen, both flammable gases that must be vented. A certain amount of gassing is expected and actually serves to circulate the electrolyte. However, excessive gassing depletes the electrolyte and changes its chemical concentration. A common maintenance task associated with flooded lead-acid batteries is the periodic addition of distilled water to compensate for water lost to gassing. Maintenance-free batteries, by the way, I'm using quotation marks with my fingers, solve this problem by catalytically recombining the gases into liquid water, over-provisioning the electrolyte, or other methods to prevent progressive loss or degradation of the electrolyte effectiveness. By monitoring the battery voltage, the charge process can determine when the battery off-gasses. Gassing typically occurs at around 2.4 volts per cell for a lead-acid battery. This means a 6-cell lead-acid battery's gassing voltage is approximately 14.4 volts. It is a recommended practice to not exceed this value for any prolonged period. The charging voltage of a lead-acid battery is affected by both the state of charge and the charge rate, where charge rate is typically expressed as a function of capacity. This can be illustrated using a graph. Consider a nominal 12-volt battery with a 20 amp-hour capacity, where capacity has been determined using a 20-hour test. This is the C20 rating. This battery could be charged at the following rates: 0.1 C20, 0.2 C20, 0.3 C20, and 0.4 C20. This means this particular battery could be charged at 2 amps, 4 amps, 6 amps, or 8 amps. If this battery was deeply depleted and only had a 10% state of charge, this curve suggests that the battery could be safely charged at the 0.4 C20 rate of 8 amps and run no risk of exceeding the gassing voltage. As the battery's state of charge increases, however, note that the charge voltage increases for the same charge rates. At a 50% state of charge, we still run no risk of exceeding the gassing voltage at the 0.4 C20 charge rate of 8 amps. However, at a 70% state of charge, we run the chance of exceeding the gassing voltage at the 0.4 C20 charge rate. This is to suggest that if the charge process is to remain efficient, effective, and safe, we must either use a lower initial charge rate or progressively decrease charge rate as the state of charge increases. The effect at higher states of charge is even more pronounced. At a 90% state of charge, we exceed the gassing voltage slightly in excess of the 0.1 C20 charge rate. Finally, at a 110% state of charge, we exceed the gassing voltage at even very, very tiny charge rates. This is to suggest that the bucket is full, and any further charge runs the risk of damaging the battery. A basic analysis of this family of curves suggests the following approaches to charging. Method 1. Play it safe. Charge only at the smallest charge rate regardless of state of charge, thereby preventing the battery from exceeding the gassing voltage for prolonged periods. This method is known as a single-step constant current charge. This method is safe, However, given such a small charge rate, one could expect this process to take all day to do so. The voltage of a deeply discharged battery undergoing a single-step constant current charge would steadily increase over a long period of time until it reached the gassing voltage above which the battery could be damaged. A partially discharged battery undergoing a single-step constant current charge would also steadily increase, only it would reach the gassing voltage quicker than the deeply discharged one. If the battery is disconnected from the load while it is being charged, and the single-step constant current value is extremely low, on the order of 0.01 C20, this might be referred to as a compensating or trickle charge, where the small current is sufficient to recharge a battery that is ordinarily used only intermittently over a long period of time. Method 2. Go big early. Charge at the largest charge rate allowable by the present state of charge, and then dial it down as the state of charge increases, thereby preventing the battery from gassing for prolonged periods. This method is known as multi-step constant current charging. This method is faster, however necessitates a slightly more complex charger. The voltage of a deeply discharged battery undergoing a multi-step constant current charge would steadily increase to the gassing voltage while in the first high current stage. Then, recognizing the gassing voltage limit, switch over to the second lower current stage, and then steadily increase to the gassing voltage, and then switch over to the third next lowest current stage and steadily increase to the gassing voltage in a quasi-sawtooth pattern. These graphs are drawn on different scales. However, note that the time it takes for 3 progressively staged currents to achieve the same level of charge will be much less than the single-step constant current method. Thus far, we've discussed battery charging only in terms of controlling current. However, voltage is an equally important property since it is the factor that directly determines current magnitude. At a very basic level, a constant voltage source could be used to charge a battery. However, this method isn't ordinarily recommended since excessively large currents can damage a deeply discharged battery. Allow me to demonstrate. Consider a nominal 12-volt battery with 100 milliohms of internal resistance. Recall from the Introduction to Batteries lecture that open circuit voltage can be used to approximate a battery's state of charge. A fully charged battery with 100% state of charge might exhibit an open circuit voltage of 12.8 volts, whereas a deeply discharged one with 0% state of charge only 11.8 volts. Assuming linearity, a battery exhibiting a 12.6 volt open circuit voltage might therefore be approximated as having an 80% state of charge. If a 12.8 volt constant voltage source charger was used to charge this battery at 80% state of charge, using Kirchhoff's voltage law, we could determine that there would be a 0.2 volt differential across the internal resistance of the battery. Via Ohm's law, current at the onset of charging would therefore be 2 amps. As the battery's state of charge increased and the battery voltage increased, the differential across the internal resistance would decrease, as would the current. At a time the battery and voltage source equal one another, the differential would not exist and no current would flow. If we were to plot current over time for a constant voltage charge, we would expect high initial current that progressively diminishes. At the end of the charge cycle, the battery begins to saturate and current drops. Lead-acid batteries require periodic full saturation to prevent sulfation, where sulfation is the buildup of lead sulfate crystals that robs electrodes of functional surface area. Full charge occurs when current drops to a set minimum level. Consider, however, a deeply discharged battery exhibiting an open circuit voltage of 11.8 volts. If a 12.8 volt constant voltage source was used to charge this battery at 0% state of charge, using Kirchhoff's voltage law, we could determine that there would now be a 1 volt differential across the internal resistance of the battery. Via Ohm's law, current at the onset of charging would therefore be a whopping 10 amps. This initial surge of current might be damaging to the battery, and for this reason, constant voltage charging by itself is not a recommended practice. This being said, if a battery could be brought to a reasonably high state of charge via other means, a constant voltage charger would be the simplest of methods to finish the charge. This is essentially the logic behind something called a float charger, where a constant voltage source is used to finish or maintain the full charge of the battery. Single-step constant current, multi-step constant current, and constant voltage charging methods present disadvantages in isolation, and ordinarily batteries are charged using a combination of these techniques. One of the most common charging method used for lead-acid chemistries is something called the modified constant voltage charging method, or the fast charge. Lead-acid batteries can't really be fast charged, so the term fast charge is somewhat of a misnomer. A complete charge takes a long time, and anything faster is a compromise. Lead-acid batteries can, however, be charged to around 70 or 80% relatively quickly. The all-important saturation charge takes up the remaining time. A partial charge is fine, provided the lead-acid battery occasionally receives a fully saturated charge to prevent sulfation. The modified constant voltage charging method is typically characterized by 3 stages and 2 important set points that define the transition between stages. First, this method uses a constant current stage, where charge current is limited to the maximum safe current allowable by the battery manufacturer. This maximum safe current value ensures that the battery is receiving a reasonable quantity of electrical energy, yet is not placed at risk of damage due to overheating or destructive effects. As can be expected, battery voltage will rise during the initial constant current charge stage. This first stage takes up roughly half of the required charge time and is sometimes known as the bulk stage, since it applies the bulk of the charge. Once the battery reaches the gassing voltage, the charger switches to the constant voltage mode, sometimes called the topping charge or absorption stage. During this stage, the battery has already been brought to a reasonably high voltage by the previous constant current stage, so the voltage differential between the charger and the battery isn't nearly as precipitous as it would have been initially. Current therefore is manageable and will decrease as the differential progressively erodes. Notice the battery during the absorption stage is maintained at or very near the gassing voltage, not over it. For a typical lead-acid battery, this might be around 14.4 volts, although you need to verify this with the specific battery manufacturer. This constant voltage stage continues with decreasing current and provides saturation. This stage ends when current has decayed to a predetermined level on the order of 0.1 C20. At this point, another constant voltage stage begins with a float value sufficient to complete the charge and compensate for the loss caused by self-discharge. Current during this third and final stage should also be small and progressively decrease down to a relative trickle that maintains the full charge. This float voltage value for a typical lead-acid battery might be around 13.8 volts, although you need to verify this with a specific battery manufacturer. Again, the modified constant voltage or fast charging method is characterized by 3 recognizable stages and 2 set points defining the transition between stages. First, a constant current stage where charge current is limited to the maximum amount allowable by the battery manufacturer. The battery voltage rises during this stage until it reaches the gassing voltage. Any further charge at this current magnitude would see voltage rise in excess of the gassing voltage and potentially damage the battery. At or near the gassing voltage set point, the charger switches to the second stage, characterized by a constant voltage. Current decreases from the previous maximum to a predetermined minimum as the voltage differential between the charging source and the battery is progressively eroded. Finally, once current has decayed to this predetermined minimum, the charger switches to a third stage, also characterized by a constant voltage. However, this time, the voltage is reduced to the float level sufficient to finish and maintain the battery charge. This combination of a constant current and 2 constant voltage stages ensure the battery is charged to capacity relatively quickly during the bulk stage and receives the saturation charge during the absorption and finishing stages necessary to ensure the long life of a lead-acid battery. As evidence of the various methods used to charge a battery, consider the following experiment. First, we'll start by discharging 3 identical 12-volt batteries with a nominal 2.3 amp-hour capacity, where capacity has been determined using the C20 test. they'll be discharged to roughly only 20% state of charge, meaning 80% of their available energy has been removed from them. The discharge curve for each battery demonstrates that while being subjected to a relatively high discharge current of 1 C20, or 2.3 amps, the battery voltage slowly drops and then dips down to a predetermined cutoff point of 9.45 volts over a period of just shy of 28 minutes. When tabulated, let's say each battery yielded roughly 13 watt-hours of energy. Notice that when the discharge period ends, the battery open circuit voltage bounces back to roughly 12 volts when the chemical reactions stabilize. This roughly corresponds to a battery with only 20% state of charge remaining. Additionally, note that with such a high discharge rate, this battery yielded only approximately 47% of its nominal 12 volts times 2.3 amp hours, or 27.6 watt-hour capacity before reaching the predetermined cutoff voltage. Those with an understanding of the battery discharge characteristics lecture will appreciate that when discharged at such high rate, this battery is behaving as expected. In fact, the only way this battery could possibly deliver the nominal 27.6 watt-hours would be if it was discharged at the comparatively slow 20-hour rate as used by the manufacturer. Now we'll take these three batteries and charge them using three different methods. First, we'll use a float charger, which is meant to simulate a constant voltage method. However, this particular float charger is characterized by a maximum current value limit. This way we won't get a damaging initial current spike. Next, we'll use a multi-step constant current charger with 4 stages. Finally, we'll use the modified constant voltage or fast charging method. Your task is to think about and predict how each method's characteristic voltage and current curves would look over time. The current limited float charger might be the hardest to predict since I've only just briefly introduced it to you. More to the point, consider how long each method would take to return a given quantity of energy to the battery. Neglecting variant efficiency concerns, let's say we're giving each method the same finish line of 13.5 watt-hours. A little bit more than we extracted. Which method do you think will achieve this result in the quickest amount of time? Here's the graph for the float charge method. Again, this isn't really a constant voltage method since it is current limited. However, it's close enough to illustrate an important point. Principally, it takes a long time to charge a battery this way. Notice it takes 15,420 seconds, or 257 minutes, or 4 1/3 hours to return 13.5 watt-hours of energy to this battery. In this case, the charger is set to float at 13.8 volts. However, sensing that the battery is initially deeply discharged, the charger limits the applied voltage to keep current below a recommended limit, in this case around 0.3 C20. As cell voltage rises, the voltage differential between the charger and the battery erodes, and the current decreases. Over time, the float charger progressively steps up the float voltage to 13.8 volts. If the float charger really was a constant voltage source of 13.8 volts instantaneously applied to this deeply discharged battery, we would have expected a large initial surge of current that might have damaged our battery. A true constant voltage method would feature a flatline voltage application and a large initial current spike that progressively erodes provided the battery survives the initial spike. Notice there's a little hiccup in the current about halfway through. This actually has nothing to do with the battery or the float charger, but rather the computer I was using to collect the data went into hibernation mode, then I had to power it back on. This really emphasizes how incredibly poor this charge method is. Even a computer, a machine designed to excel at performing boring tasks, got bored and fell asleep watching this battery charge. Let's try a different method. Here's the graph for the multi-step constant current charge method. In this case, the charger uses 4 distinct constant current charge stages. Stage 1 is characterized by a 0.4 C20 charge rate. In this case, 0.4 times 2.3 is 0.92 amps, or 920 milliamperes. The charger maintains this charge rate for quite some time, and during this time, the battery voltage steadily rises to the gassing voltage of 14.4 volts. Any further charging at this rate could potentially damage the battery. Recognizing this limit, the charger switches over to the second constant current stage, characterized by a 0.3 C20 charge rate. In this case, 0.3 times 2.3 is 0.69 amps, or 690 milliamperes. The charger maintains this reduced charge rate for a comparatively short period, during which the battery voltage again steadily rises to the gassing voltage of 14.4 volts. At this point, the charger switches over to the third constant current stage, characterized by a 0.2 C20 charge rate. In this case, 0.2 times 2.3 is 0.46 amps, or 460 milliamperes. The charger maintains this reduced charge rate for a comparatively short period, during which the battery voltage again steadily rises to the gassing voltage of 14.4 volts. Finally, the charger recognizes it has hit the hard limit again and switches over to the fourth and final constant current charge stage, characterized by a 0.1 C20 charge rate. In this case, 0.1 times 2.3 is 0.23 amps, or 230 milliamperes. The charger maintains this reduced charge rate, and the battery voltage again steadily rises to the gassing voltage of 14.4 volts. Using this method, our predetermined finish line of 13.5 watt-hours of energy is reached in only 4,060 seconds, or 68 minutes, just over an hour. Using a slightly more complicated charger with a higher initial current, we effectively reduced our charge time to a quarter of our previous attempt. This is a good thing. Let's see if the modified constant voltage, or the fast charge method, can meet or beat this record. Here's the graph for the modified constant voltage or fast charge method. Note this method is characterized by 3 distinct stages and 2 important set points. Stage 1 is characterized by a constant current. In this case, the charger is limited to 0.4 C20, or 0.92 amps, or 920 milliamperes. This is essentially identical to the first stage of our earlier multi-step constant current charge method. Similarly, voltage progressively rises during this stage until it reaches the predetermined gassing voltage set point of 14.4 volts. Sensing this set point, the modified constant voltage charger switches to a second stage characterized by constant voltage equal to the gassing voltage. We can zoom in on the voltage graph to make this more evident. During the constant voltage stage, current progressively decreases. Finally, when current decays to a predetermined value, the modified constant voltage charger switches to another constant voltage stage characterized by a 13.8 volt float value. Current progressively decreases. Although I've extended the graph out to 5,760 seconds, so you can see all 3 stages for the modified constant voltage method, this method crosses our predetermined finish line of 13.5 watt-hours at 4,410 seconds, or 73.5 minutes. This method, despite the title Fast Charger, actually took a little bit longer, 5.5 minutes longer to be exact, than our previous multi-stage constant current charger. What gives? Here's what gives. That's not how you ordinarily charge a lead-acid battery. This is how you ordinarily charge a lead-acid battery. Notice that when we place both methods' energy delivery in units of watt-hours on the same graph, yes, the multi-stage constant current charger in brown actually hits the 13.5 watt-hour finish line a little earlier than the modified constant voltage method in green, only because the modified constant voltage method backs off on the current during the second stage. This means energy delivery does slow down. However, notice the modified constant voltage method keeps the battery at the gassing voltage during the absorption stage for a period, whereas the multi-stage constant current charger does not. This is to suggest that a battery exclusively charged using the multi-stage constant current method might not ever reach the all-important absorption stage and may not have as long a lifespan. To be sure, other charge methods and hybrid combinations exist. However, when you get right down to it, the modified constant voltage method, characterized by 3 distinct stages, is the simplest of the methods that yields the best results: a fast charge and a long life. Notice both first stages are essentially identical. They're both constant current stages, limited only by how much the battery can handle. The modified constant voltage method simply eases off the gas at the very end of the trip and coasts to a gentle stop. Before we wrap this lecture up, Let me briefly mention charge efficiency and the equalization process. Charge efficiency is the ratio of the energy actually put to good use over that supplied by the charger. Obviously, not all the energy supplied by the charger goes into beneficial energy storage, and some of it is lost to heat, destructive chemical processes, or other losses. However, you might be astounded to learn that the charge process can be very, very efficient. This graph of charge efficiency as a function of state of charge shows that only during low states of charge and as the battery approaches a full state of charge is the charge process actually considered inefficient. Therefore, my arbitrary finish line of 13.5 watt-hours for all three experiments is slightly inaccurate, since it assumes all 13.5 watt-hours are identically put to good use by the three different charge methods. This being said, for regions between 10 to 90%, we can assume most of the energy delivered by the charger is being put to good use. Charge efficiency can also be plotted as a function of applied voltage and charge rate. For a nominal 12-volt battery, note that voltages below 12.1 volts aren't efficient because the charge voltage is not high enough to support the charging reaction. Efficiency decreases for high voltages due to increased destructive currents. At high charge rates, efficiency shows a notable decrease because the surfaces of the plates become fully charged and results in increased voltage and gassing. At very low charge rates, efficiency drops because the charge current is equivalent to self-discharge rate. A final consideration about charge efficiency is that it is also temperature dependent. These curves are valid only for constant temperature conditions, and other temperatures necessitate the use of different curves. Lastly, equalization is essentially a periodic controlled forced overcharge for the purposes of removing sulfation. This is a periodic maintenance procedure and extends the lifespan of a battery. Applying an equalizing charge every 6 months or after about 20 cycles brings all cells to similar levels by increasing the voltage to approximately 2.5 volts per cell, or 10% higher than the recommended charge voltage. During equalization, batteries must be kept cool and under close observation for unusual heat rise and excessive venting. This brings the battery charging lecture to a close. Before we say goodbye, take one moment to consider the time differential not only between the different charge methods, but also between the discharge and the charge period. At the beginning of our experiment, we discharged 3 identical batteries over a period of only 28 minutes. It took the float charger close to 4.5 hours, the multi-stage constant current charger 63 minutes, and the modified constant voltage charger 73.5 minutes to return just a little bit more than we extracted. The imbalance between available output and required input is obvious, especially considering we discharge the battery at such a rapid and inefficient rate. This is to suggest that building something up takes a lot more time than wrecking it. Let this be a cautionary tale to those of you that daily struggle to stay inside the lines. I'm not saying to never get crazy and have some fun, but I am saying that when you do, be prepared to spend lots of time getting yourself back on track. In conclusion, this lecture discussed battery charging methods. We discussed single-stage constant current charging, trickle charging, multi-stage constant current charging, constant voltage charging, float charging, the modified constant voltage or fast charging method, charge efficiency, and equalization. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.